Okay, it's week 3 Wednesday. This I guess marks our halfway point in our quarter, our summer session. And so maybe um just want to do a just check in with you guys briefly and just get a sense of how you guys are doing, how you guys are feeling about the course or just things in general. I don't know if anybody had anything to say or want to. Or you can just be quiet, I guess. Okay, all right. I got one thumbs up. Thank you for that. All right, a few more thumbs up. Thank you. Appreciate that. So I guess that's a good sign. You feel okay about the course content, the pacing. I don't know, all of that stuff is feeling okay. Yeah, any feedback you have, I'm happy to listen. Last quiz a little bit lengthy. Yeah, some of the some of the stuff will be, as we go through course material, everything kind of builds up on top of each other, right? So this stuff on hypothesis testing builds up on stuff from sampling distributions, and that builds on normal distributions, and that builds on probability. And so everything kind of continues to build up. And so, there's just a lot more stuff to have to, kind of keep track in your brain. And certainly that can present challenges. Don't feel too bad. I just published the grades for quiz 2, so that those just went live. You can take a peek there to see how you did. But all right. Well, we'll continue on here. And so, yeah, we are going to discuss more on hypothesis testing today. We introduced hypothesis testing on Monday as kind of maybe the other side of the coin for confidence intervals, at least when we're talking about the T-test. And then there's a lot more to cover kind of conceptually. And so we'll spend a large portion of today's lecture covering that. Okay, and so when we conduct our T-test for independent samples, and that we are comparing the means of two populations based on what we observe in two samples, we always start off by writing a testable hypothesis. And the null hypothesis will always have an equal sign. And because we're comparing two means from populations, our null hypothesis is always going to be mu1 is equal to mu2. That's always going to be our null hypothesis. And then the alternative is going to be mu1 doesn't equal, or mu1 is greater than, or mu1 is less than mu2, right? And whether we use a not equal sign or a greater than or less than sign depends on the question that's written, and whether we're interested in just a plain old difference, or if we're interested to see if population 1 is greater than population 2, or the other way around, okay? And then we always kind of start off and we say, well, you know what, let's assume that the null hypothesis were true. And if that were the case, what would our world look like? What would this hypothetical situation look like? And if the null hypothesis were true, if mu1 were equal to mu2, when we take two random samples, we expect their sample means to be equal to each other, at least similar to each other. We would expect y bar 1 and y bar 2 to be about the same size. And they're, even if the null hypothesis were true, they're unlikely to be exactly the same size. And so we calculate our test statistic, which is how different is y bar from y bar 1 from y bar 2. We calculate the difference between y bar 1 and y bar 2, and we say, is that a big difference or a little difference? And that depends on how large the standard error is. Okay. And once you do that, you look that up in your t-table, And that will give you a sense of how unusual it is. Is this an extreme value? Is it something that's not all that uncommon? You find the area in the tails, and that'll give you a p-value, and then we can make our decision based on that. Okay. We said the p-value, again, is the probability of observing the statistic in our data. In our case, the statistic is the difference between y bar 1 and y bar 2. The statistic in our data, or something more unusual, if we assume that the null hypothesis were true, if we lived in this hypothetical world. Okay. And for the t-test, the p-value is going to be equal to the area in the t-distribution that's in the tail beyond the test statistic. And if it's a non-directional test, if it's a two-sided test, then you're going to kind of find your tail area and multiply it by 2, because it's symmetric, and you want to find the area in both of those tails. All right, and so just to kind of recap everything, the null hypothesis makes a claim about the population. We test this hypothesis against our data. We go through the steps to calculate our p-value, and then ultimately we compare the p-value to our significance level alpha. If the p-value ends up being less than alpha, then we say the p-value is small, and that leads us to reject the null hypothesis. And if the p-value is greater than alpha, then we say the p-value is large, and we will not reject the null hypothesis. Okay. And so we have to, again, the phrasing and what we're allowed to say is very specific. And I saw a few questions on CampusWire about this. And so hopefully I'll try to address those questions here. Basically, if the p-value we get is small, then that means the test statistic we observe, in our case, the difference between y bar 1 and y bar 2, is considered to be extreme if the null hypothesis were to be true, right? So if the null hypothesis were true, we expect y bar 1 and y bar 2 to be equal and to have a difference of 0, and maybe we observe a difference of 12, and then we would say that's a really unusual or really extreme value. Okay. Especially if you when you compare that to the standard error. Okay. And so the fact that we did actually observe this really extreme or unusual value in our data indicates to us that, probably what's going on is that our null hypothesis is wrong. Okay. And so if we do end up getting a small p-value, our decision is going to reject the null hypothesis. Now, that isn't to say that this definitely means that the null hypothesis is wrong. It is still technically possible, right? It's still technically possible that the null hypothesis is true, and that we happen to get this value by random coincidence. That's still possible, right? For example, you could flip a coin, and if you observe the coin landing 10 heads 10 times in a row, you'd say, man, that's so strange. This coin probably isn't a fair coin. It's, some kind of trick coin or a rigged coin so that it lands heads more often, right? If you flip the coin and you get heads 10 times in a row. Now, and that would be a reasonable conclusion, but it is also, it's also possible that the coin actually is fair and you happen to get 10 heads in a row by random coincidence. We're going to say that wasn't the case. We conclude that wasn't the case because getting 10 heads in a row is happens in about 1 in 1,000 times, but it's also possible that it happened 1 in 1,000 times, right? So what we're saying is that, I'm willing to reject the idea that the coin is fair just because getting 10 heads in a row is really, really, really unlikely. Okay, it only happens 1 in 1,000 times. But it's also possible, it's technically possible that it actually is a fair coin and we just happen to get this really unusual thing. We're just saying, because it's so unlikely, we're going to reject that. Okay, we have a question. It says, let's say alpha is 5% and the p-value is smaller than alpha. Can we interpret this by saying that there's a probability of less than 5% that the null hypothesis is true? Ooh, okay. So the answer is that interpretation is not correct, and so I'll give us a few examples of how to properly interpret the null hypothesis. Okay, the null hypothesis will never be able to tell us the probability of, the p-value does not tell us the probability that the null hypothesis is true or false. Okay, we're not asking about the probability that the hypothesis is true. We're asking, it answers the question, what's the probability of getting this data if the hypothesis were true? It's a difference, and it, I'm saying all of these words, right? And at some point it just sounds like gibberish, but the p-value does not state whether, it is not an expression of probability on whether the hypothesis is true or not, okay? And again, it's kind of one of those situations where in reality, the hypothesis either is true or it's not true. We don't know whether it's true or not, okay? Either the hypothesis is true or it's not true. So we can't really have a expression of probability about the hypotheses, right? So, we can talk about, there's some kind of trial, right? And there's a defendant for a criminal trial, and we ask, did the defendant actually commit the crime or not? Okay, that's what the jury's supposed to figure out. Now, in reality, the truth is that the defendant either is guilty or the defendant is innocent. And it doesn't make sense to talk about what's the probability that the defendant is innocent or what's the probability that the defendant is guilty. Okay, so we can't really talk about probability of the hypotheses. What we can say is that if the defendant were innocent, it's really, really, really unlikely for us to end up with this evidence that we have. If the defendant actually were innocent, it would have to be a very weird string of coincidences where we would find, blood of the victim in the defendant's house or on their clothes or something like that, right? That would be, we would say, it's possible just through some weird coincidence that like this and that happen, and it's a possibility, but it's also, unlikely, right? It's unlikely, and that's basically what the prosecution tries to say. It's trying to say that look at all of this evidence. How could we get this evidence if the defendant actually were innocent? And they're trying to convince the jury or the judge that because the evidence is so compelling that they have to conclude that the defendant is guilty or something like that. And so the p-value is not it will not give us a probability of whether the null hypothesis is true or false, because the null hypothesis either is or isn't true, and we can't talk about probabilities here. It's the p-value is the probability of getting our data if the null hypothesis actually were true. And we're saying if the null hypothesis were true, it's really either really unusual to get this data, and therefore we believe the null hypothesis is false, or maybe it's not that unusual. Okay, and so the flip side of this thing is we get a large p-value. All right, and if you get a large p-value, then that means the data that we have observed could easily be produced by randomness while the null hypothesis were true. Okay, so even if the observed data doesn't exactly match what the null hypothesis says, it's not considered to be an unusual outcome, right? So the null hypothesis says that the two populations have the same mean. And so when you take a look at your data, maybe your two samples have means that aren't exactly the same. You get y bar 1 is 1.3 and y bar 2 is 1.4. And so they're not exactly the same. You get a difference of 0.1. But you do our calculations and it says, yeah, you know what? Getting a difference of 0.1 is not unusual. Okay, it's not unusual even if the null hypothesis were true. And so if we end up getting a large p-value, we'd say our decision is not to reject the null hypothesis. Okay, and we don't say we accept the null hypothesis. We say we don't reject it. Okay, so yeah, the question says if we do not reject the null hypothesis, can we say we support or accept the null hypothesis? And the answer is no. Okay, we have to say we do not reject the null hypothesis. We cannot. We do not say that we accept the null hypothesis. So we have to. There's all of these like legal rules about like what we're allowed to say, but yeah, maybe I'll give you a few more examples, and maybe hopefully this will make sense. But yeah, this is we end up using a lot of double negatives, all right, and it feels a little bit strange, but we kind of have to keep it that way because saying the other thing without the double negatives might be saying too much, right? So we say, we don't have evidence that there is a difference, or so if you say we don't have evidence that there is a difference, is not saying the same thing as we have evidence that they're the same. Okay, maybe I can type this out, right? So I didn't put this in the notes, but if I write, so if you say do not reject 0, that means we would say we do not have evidence that there is a difference, between the two means. Okay, but you can't say this means that the two means are the same. So yeah, not rejecting, okay, allowed. Do not reject the null hypothesis. Not allowed. Accept the null hypothesis. Right. And this, it feels like, why am I allowed to say one thing but not the other? But these are the limitations of what we can say. Is that right? Are you guys able to see this text okay? Okay. All right, so there are errors inherent to the hypothesis testing process. These are unavoidable, okay? We cannot completely avoid these. Anytime we are making conclusions about the population based on a sample of data, basically all of statistics or inferential statistics comes down to, you're looking at one thing, we're making assumptions to fill in our knowledge about the rest, right? And we have to do this throughout all of life, right? We don't have the time and luxury to learn every detail about everything. And so we always have to kind of make some assumptions to fill in the rest, to fill in the blanks, okay? But we also know that when you make assumptions, sometimes you're wrong, okay? And sometimes you make a mistake and you end up getting it wrong, right? And this is inherent to statistics. We are looking at a sample of data. Based on what we see in our sample of data, we're making conclusions about the population, even though we didn't observe the population directly. And so there are inherent mistakes that we cannot avoid, right? We want to avoid these, but we cannot, because anytime we make conclusions based on just a sample, we can make a mistake, right? And so there are two types of errors. Now, as people were discovering statistics or establishing it as kind of an area of study, they realized, oh, there's two types of mistakes we can make. And at the time, they didn't come up with good names. They literally named this type 1 and type 2. That you have error type 1 and error type 2. And these are like basically the worst names you could come up with for something, right? If you have two types of things, okay, well, what do we call these things? Oh, let's call this type 1 and let's call this type 2. Okay, they are not good names. Later on, we came up with better names that I think make more sense. But unfortunately, the original names, type 1 and type 2, have kind of persisted through the literature, okay? The type 1 error, later on, we decided, oh, you know what? It makes more sense to call this the false positive. And so we can call the type 1 error the false positive, but it's also known as the type 1, okay? And this means we have rejected the null hypothesis. Our decision, based on the data we see, our decision following the process, okay, is that we are going to reject the null hypothesis. But that's a mistake, right? You looked at the null hypothesis, you look at the data, you say, all right, based on this, we're going to reject the null hypothesis. But in reality, the null hypothesis actually is true, and we should not have rejected it. Okay, so that could happen, right? And then the other is the type 2 error. That's the false negative. The false negative. This is we mistakenly do not reject the null hypothesis, but in reality, the null hypothesis was false. We should have rejected it, but we did not reject it. Okay. So you have the false positive and you have the false negative. Okay, that's the type 1 and the type 2 error. So a type 1, a false positive, again, this is we reject the null, but in reality, the null hypothesis is true. We shouldn't have rejected it. So let's say you do a study, your p-value ends up being 4%. Alpha was actually 5%. And so we say, well, because my p-value is less than alpha, what we're going to say is, well, according to my significance level, the probability of getting my data is unusual or is low if the null hypothesis were true. And so therefore, we're going to conclude that the reason why I got this data is because the null hypothesis is wrong. Okay, and that something else is going on, and that explains how I got this unusual data. All right, so we conclude that the null hypothesis is wrong and we reject it. But in reality, it turns out the null hypothesis actually is true, and the data we observed was really just a random fluke. Sometimes that happens, right? Again, we could flip the coin, we get 10 heads in a row, we say, oh, that must be a trick coin, okay? All right, and that's a reasonable thing to conclude if you see the coin land heads 10 times in a row. But it could have been that it was actually a fair coin, and we just happened to witness this very rare occurrence where you got 10 heads in a row, okay? Even something like getting 7 heads in a row, right? If you do, what's the probability of getting 7 heads in a row? You know, I think that's like 1 in 128, less than 1%. I think if you see 7 heads in a row, you'd say, oh yeah, it's probably a trick coin. It's probably something strange, but it could happen by just random chance. It's possible, right? And so in this case, our decision to reject the null hypothesis when in reality was correct, we call that a type 1 error. That's known as a false positive. Okay. The other type of mistake is the false negative, right? We don't reject the null hypothesis. That's our decision. We look at the data and we go, oh yeah, you know, this data could have been the result of just random chance if the null hypothesis were true. So we're not going to reject the null hypothesis, right? But in reality, the null hypothesis was wrong. We should have rejected it. We should have rejected it, okay? So maybe we do our calculations. Our p-value ends up being 7%. Our alpha was 5%. So in our case, because not our data, our p-value is greater than alpha, we choose not to reject the null hypothesis. And in this case, we say the data we've observed isn't that unusual enough for us to doubt the truth of the null hypothesis. Okay, but it's possible, all right? It's possible that the null hypothesis actually is wrong and that we should have rejected it. And if that's the case, then we have committed a type 2 error or a false negative, okay? Oftentimes your type 2 error is the result of not collecting enough data, right? It could also happen if there's some random fluke that produces misleading results, okay? So for example, you could actually have a coin that's unfair, right? A coin that's unfair, and maybe long-term it lands heads more often than tails. But then when you flipped it 20 times, maybe just by random chance, you happen to get 10 heads out of 20. And you go, oh, 10 heads out of 20, that sure seems like a fair coin. So I'm not going to reject the null hypothesis. We're going to say, we don't have any reason to believe that it's an unfair coin because I got 10 heads out of 20. Okay. Now remember, we're not concluding based on getting 10 heads out of 20 flips that the coin is definitely fair. We're just saying I have no reason to doubt that it's a fair coin. Okay, I have no reason to suspect that it's an unfair coin, but it could actually be an unfair coin. All right, is that okay? So this is the table. This is what we want. We want the correct decisions. If the null hypothesis were true, what we want is our decision to be don't reject the null. And if the truth is that the null hypothesis is false, the correct decision will be to reject the null. Okay. But then if the null hypothesis were true and we reject the null, that's known as a type 1 error or a false positive. And if the null hypothesis were false and our decision is not to reject, that's the type 2 error or the false negative. Okay. Question, is there error associated with alpha since it's arbitrary, even if it's normally 5%? Yeah, so that's actually my very next slide. The significance level we choose, alpha, right? So we often choose alpha as 5%. This is equal to the probability of committing a type 1 error, right? Because we are going to reject the null hypothesis anytime our p-value is less than alpha. So if you come in with an alpha of 5%, we're basically saying anytime my p-value is less than 5%, we're going to reject the null hypothesis. But if you think about it, how often is the p-value going to come under 5%? When the null hypothesis is true, well, the p-value is going to end up being less than 5% of the time, even though the null hypothesis is true. So you're going to get a small p-value, quote unquote small p-value with a probability of alpha, even when the null hypothesis is true. So whatever alpha you choose, 5%, that is your accepted risk of type 1 error. So if you choose alpha 5%, we're basically saying, I'm okay with committing a type 1 error 5% of the time, right? It feels a little bit strange, but if we pick alpha equal to 5%, we're saying, I'm okay with making a type 1 error 5% of the time. Okay. Now you might say, well, actually, I'm not okay with that. I don't want to commit a type 1 error, right? I don't want type 1 error. That sounds pretty bad. A false positive, I don't want that. So you can reduce your risk of type 1 error by picking a lower alpha, right? And you can say, well, let's use alpha 1%, okay? And so now you will reduce your risk of type 1 error to only 1%. And you say, well, why should I accept a 1% risk? I should go even lower. Half of 1%, 1 in 1,000. Why not just do 0? Can't I just eliminate the risk of type 1 error? Well, you can't fully eliminate it, okay? Because whenever you reduce your alpha, okay, what you're basically saying is, I'm going to need more evidence. I'm going to need stronger evidence before I reject the null hypothesis, because I don't want to mistakenly reject the null hypothesis. So before I reject the null hypothesis, I got to see a lot of evidence. Okay, so the problem there though is that if you choose a lower alpha to reduce your risk of type 1 error, you are inherently going to increase the risk of type 2 error, right? This is you can meet maybe some friends that have we each have different kind of levels of giving people the benefit of the doubt, right? So for example, you and your friend, maybe you have different levels of giving the person the benefit of the doubt. Maybe you meet somebody who says, hey, you know what, let's hang out or something, right? You decide to go hang out, and this person does something a little bit strange, right? Maybe they say a joke that was a little bit offensive, or they're rude to the wait staff at a restaurant or something, right? And one person can just say, that's enough. I don't want to have anything to do with this person anymore, right? And then somebody else could say, you know what? Let's give this person the benefit of the doubt. Let's give him another chance or something, and something like that, right? And there's a couple of possibilities, right? It could be that this person is a terrible person and we should never hang out with this person, and and that's it, okay? Or it could also be that this person is not a bad person or anything like that, is actually worthy of being a good friend and just that day, happened to do some weird things that were a little bit of out of character or something, right? And so, you could go through life either quickly rejecting people, okay, right? And that would be somebody who operates kind of with a large alpha. It only takes a little bit of evidence for you to say, man, I'm rejecting this person, okay? And so the downside of that is you're going to have a lot of false positives. You're going to be rejecting a lot of people who might actually be decent people, okay? The flip side is you could also operate with a low alpha, right? You could choose a very small alpha, and you're going to say, you know what? It's going to have to take a lot of evidence before I'm going to say this is a bad person. I'm going to reject this person, okay? And the risk there is you end up hanging out with people that are not good people, and it's like, how many incidents is it going to take for you to come to realize like this was actually a bad person that we shouldn't have spent any time with, okay? And so the flip side, right? You can say, well, I don't want to, I want to give people the benefit of the doubt. I don't want to just reject someone just because they're having a bad day or something like that, right? I need stronger evidence to convince me before I'm going to reject this person, reject the null hypothesis, right? And so the downside of that is that you're going to be committing type 2 error a lot more. You're going to be hanging out with people that, just weren't that great to begin with a lot longer for you to realize, okay, should have rejected this person a long time ago, okay? So you, I don't know how I got off on this tangent here, but when you're doing like experimental research and stuff like that, okay, you, the researcher, gets to choose the level of alpha to use, right? And you, throughout your life, when meeting people, you get to choose what level of alpha you want to use, right? Whether you use a large alpha or small alpha depends on the situation and whether the consequences of making a type 1 or type 2 error is worse. So you have to think about, what's worse? Is it worse to kind of reject a perfectly nice person, or is it worse to hang out with a person that wasn't that great to begin with, right? And you have to think about that, type 1 or type 2 error, right? So, all right, let's change the scenario here. Okay, so here's the scenario. We're going to say a patient visits a doctor for a disease screening, okay? And so we have to think, okay, well, how does this work, right? So generally, the doctor is going to kind of assume that the patient is not suffering all kinds of ailments, right? Unless they show some symptom of illness, right? So number one, patient is healthy is the null hypothesis. The alternative is that the patient is sick. And in reality, either one of these things is true. The patient is actually either healthy in real life or the patient is sick in real life. Now, what we want, okay, this is the ideal scenario. We want everyone who is healthy visits the doctor, and the doctor says, yep, you're healthy, go home. You got nothing to worry about, okay? And then if somebody is sick or needs medical attention, the doctor is going to say, oh, glad you came in. We caught this thing. Let's get you treated for it, okay? That's what we want, okay? But this doesn't always happen this way, okay? Sometimes we commit a type 1 error, and sometimes we commit a type 2 error. What would a type 1 error be in the context of this situation? Anybody? Okay. Yeah, so type 1 error would be saying that a healthy person is sick, okay? A healthy person either gets medical attention, the doctor says, oh, you know what? This came up in our charts, let's give you some more tests or something. A type 2 error, though, would be a sick person is sent home, right? A person who's actually sick, a person who needs medical attention, the doctor says, oh, there's nothing wrong with you. Just go home, okay? What kind of which error is worse? The type 2. The type 2 error is worse, right? Okay, because the type 2 error, especially if the person has a contagious disease, if they're cleared and sent home, they could end up, spreading the disease to other people. Or if it's something that, progressively gets worse, right? This person has, like, I don't know, a cancer or a tumor or something, and the doctor says, oh, you're fine, they might go home and then things get worse and it could turn into something that's, much more dangerous or even life-threatening later, okay? So I don't know if you guys ever go to WebMD when you're sick and you're looking up symptoms, but there's kind of a joke where anytime you type something into WebMD, you type your symptoms into WebMD, WebMD comes back and says, you know, you have cancer, you're gonna die or something, and you need to go see the doctor, okay? And it's not that WebMD is trying to scare people, okay? That seems like WebMD is maybe trying to scare people, but what WebMD is just operating with a very large alpha, okay? Because the type 2 error is worse than the type 1, we want to pick a large alpha. We would rather make type 1 errors, right? Large alpha means we're going to make a type 1 error. We're going to have more false positives than false negatives. We'd rather make false positives than false negatives. And so WebMD operates with a very large alpha. And basically WebMD's premise is that, you know what, what are the consequences of having a false positive when somebody uses WebMD, okay? The consequences of a false positive with WebMD is maybe a little bit of anxiety, but it's not like you can go get a prescription for medication based on your WebMD diagnosis, right? Maybe you would have to go to the doctor's office, and then the doctor says, oh, no, you're fine. But the consequences of a type 2 error could be, you know, much worse, right? Somebody could actually have a cancer or a life-threatening condition, and that type 2 error would be that this person doesn't get the medical attention that they need, okay? And so in that case, WebMD just only requires a little bit of evidence before they reject the null hypothesis. Now, a type 1 error could be bad if we're talking about some extreme medical treatment, like starting, say, chemotherapy, which is, uses these drugs that are very, very harsh on the body, right? They're used to kind of kill off cancer cells, but also it destroys a lot of healthy cells. So they're very harsh on the body, or other things like surgery or something like that. And so a doctor is not going to just you're not going to just walk into the office and the doctor immediately says, oh, okay, we're going to start you right away on this very drastic treatment. You go through a series of tests, right? Before they subject you to, say, chemotherapy or surgery or something like that, the doctor is going to give you a series of tests and biopsies and things like that, just to make sure that this is the right treatment. So when we think about what are the consequences of a false positive, as those consequences get harsher and harsher and worse, we try to reduce the level of alpha by having more and more tests to kind of make absolutely sure that this is the right treatment to use. Okay, so in the kind of the medical system, there's kind of these systems in place to kind of make sure that we don't commit a type 1 error if the consequence of a type 1 error is bad, and we also try to avoid type 2 errors, right? Okay. The flip side, and we kind of mentioned something like this. This would be a situation where the type 1 error, I think, is worse. Okay, so we could think of a criminal trial, and in general, we're going to assume, or at least the way the American justice system is set up, is that we assume defendants are innocent until proven guilty, right? And this is how it should be. And so the null hypothesis here is that the defendant is innocent, and the alternative is that the defendant is guilty. Okay, either one of these things must be true. Okay, and in the ideal scenario, what we want is we want everyone who is innocent. We want innocent people to be acquitted and not to be convicted, right? And we want anybody who's guilty. Okay, we demand justice, and we want guilty people to be convicted. Okay, that's what we want, right? We would consider these errors, we would consider these things failures of the justice system. Failures of the justice system. One would be a false positive. A false positive would be that an innocent person is convicted. An innocent person is sent to prison or possibly worse for a crime that they did not commit. Okay, and a false negative would be that a guilty person is acquitted. A guilty person is let go. Okay, both of these things are considered failures of the justice system. And, there's always a little bit of debate as far as which one is worse, But the way our justice system is set up to say that the type 1 error is worse, that we do not want to convict innocent people. That is a worse travesty than letting a guilty person go free. All right. And in that case, then that means we should pick a small alpha. Okay. We should pick a small alpha, right? It takes, and so if we have a small alpha, okay, that means we need a lot of evidence before we reject the null hypothesis, okay? And we kind of use a phrase in that says use a small alpha. That the judge doesn't tell the jury use a small alpha, but they say, make sure you are convinced beyond a reasonable doubt, okay? They don't want the jury to convict the defendant because of a hunch or a gut feeling, but they want that the evidence to be convincing beyond a reasonable doubt for the before the jury comes to a guilty verdict here, okay? And also note that when the jury delivers their verdict, it's either guilty, meaning they've rejected the null and accepted the alternative, or not guilty, meaning they did not reject the null hypothesis, okay? The jury will never come to the conclusion that the defendant is innocent. The jury never says, we find the defendant innocent. They just say, the defendant is not guilty, right? And that's a difference, right? They're saying not guilty is not the same thing as saying that the defendant is innocent. It's just saying there wasn't enough evidence to convince the jury of a conviction, okay? A question in the chat. It says, how are you making the statements for type 1 and type 2 error? A little confused on that part, right? So type 1 error, false positive. False positive means we've rejected the null. Okay, what does it mean to reject the null? Okay, is that if we reject the null, that means the jury comes to a guilty verdict, right? A jury convicts the defendant, okay? So type 1 error, false positive, we rejected the null, but in reality, the null hypothesis is true. So the jury rejects the null, convicts when the null hypothesis is true, when the defendant actually is innocent, okay? The type 2, the false negative, means the jury did not reject the null, okay? The jury says, we do not make a guilty verdict, right? We say, the jury says, the jury finds the defendant not guilty, but in reality, the null was wrong, the alternative is true. In reality, the defendant actually is guilty, should have been convicted, okay? But that guilty person is let go, right? And we want to avoid both of these things, right? We don't, especially for when we think of families of the victims and things like that, the victims want justice. They want to see the guilty person to be convicted. They want justice for that, okay? And so both of these things we want to avoid, but the way our system is set up is we really want to avoid convicting innocent people, right? If somebody didn't actually commit a crime, we don't want to imprison that person, okay? And or possibly even worse, right? In some cases we have capital punishment, death penalty cases, and the idea of executing an innocent person is anathema. It's something that we really don't want to be guilty of as a society. And so that it's so that would be one of the arguments against having capital punishment to begin with, is that, again, you cannot completely eliminate the risk of type 1 error. The only way to eliminate the risk of type 1 error is to never reject the null hypothesis, right? So you could say, I want to reduce my risk of type 1 error by having alpha equal to 0, okay? But having alpha equal to 0, because alpha being the probability of type 1 error, alpha equal to 0 means your p-value will never be less than alpha. You will never reject the null hypothesis, right? Because The only way you reject the null hypothesis is if your p-value is less than alpha. And if your alpha is 0, your p-value will never be less than alpha, which means you will never reject the null hypothesis. And that's really the only way you could completely avoid a type 1 error, right? And so, I'm not trying to get into some ethics debate here, but one argument against the death penalty and capital punishment is just that as a society, we don't want to ever execute an innocent person. And there have been cases where people who have been on death row, who have been convicted and were scheduled to be executed, later on evidence came forward and they were exonerated. And it was found that that person was not guilty of the crime. And so the idea of executing an innocent person, the only way we can completely avoid the possibility of executing an innocent person is to never execute anyone. Okay. And that means you will commit type 2 errors. And if there were such a person that, again, not to get into an ethical debate, but are there some people that deserve to be executed or something? A type 2 error would mean somebody who deserves to be executed does not get executed, and that's that's again not trying to stir up the pot here with statements like that. Okay, but the only way you could completely avoid type 1 error is to never reject the null hypothesis, and that's a question that you have to consider there. Okay. I've realized I've completely forgotten to give you view quiz answers. Let me go ahead and give you 2 of your view quiz answers for today. So your first 2 view quiz answers for week 3 Wednesday are the letters E and B. So number 1 is E as an elephant is your first view quiz answer, E as an elephant. And the second view quiz answer is B as in bear. B as in bear is the second view quiz answer. Okay. So again, first view quiz answer is E as an elephant. Second view quiz answer is B as in bear. I'll give you your third view quiz answer later. All right, does that kind of make sense for type 1 error, type 2 error, whether we want a large alpha or a small alpha in these situations? Okay. This is a little bit of, I guess, stats humor, if there is such a thing. We could say the null hypothesis would be that the patient is not pregnant. And so a type 1 error, the false positive, would be the doctor telling this man who is not pregnant, the doctor telling this person, you are pregnant. And the type 2 error, the false negative, would be telling the this woman who was at least supposed to be clearly pregnant in the picture, the doctor would say, you are not pregnant, right? And so these are type 1 and type 2 errors here, okay? And so from a medical standpoint, the type 2 error is worse. We want to make sure that people who are pregnant are getting the medical treatment and medical care that is appropriate for a pregnant person. But in a conversation with a friend in a social setting, a type 1 error is considered to be a very, very bad error. And so that's what we have. And speaking, it's and depending on the context, I've gone to doctor's appointments with my wife, and just kind of very as soon as you check in, you fill out some questionnaires, and a lot of these questionnaires, one of the questions right off the bat is, are you pregnant? Are you currently pregnant? Right? And there's no in that context, there's no one is offended by asking, are you pregnant in the context of a medical situation, because we understand, right? There's something inherent that understands that, oh yeah, a type 2 error would be bad if the doctor doesn't recognize that someone is pregnant when they actually are pregnant. That would be a bad situation, right? But in a social setting, we also know it's not appropriate to ask somebody if they are pregnant, because effectively it's making a comment about their appearance or something. And so, you generally, to avoid type 1 error at all, is you just don't even ask anybody if they're ever pregnant until they tell you, right? So that's that. Okay. So we talked about alpha being the significance level, alpha being the probability of making a type 1 error or a false positive. So we said the probability of committing a type 1 error is alpha. And the probability of committing a type 2 error is denoted by the symbol beta. Beta is the probability of making a type 2 error, okay? And alpha is the first letter of the Greek alphabet, and beta is the second letter of the Greek alphabet. And so type 1 goes with alpha, type 2 goes with beta, okay? Alpha looks like an A, beta looks like a B. So first letter being A or alpha, second letter being B or beta goes there. And that's actually where we get the name alphabet for, you know, alpha and beta, the first two letters of the Greek alphabet comes together there. The power of a test, okay? There's a term called power that is known as 1 minus beta, right? The power is 1 minus the probability of making a type 2 error. So this is power would be equal to the probability of not making a false negative. So this sounds really strange. What's the probability of not making a false negative? So not making a false negative means we are going to correctly reject the null hypothesis when we're supposed to reject the null hypothesis. Okay, that's known as the power of a test. The power of a test is the probability of correctly rejecting the null hypothesis when we are supposed to reject the null hypothesis, okay? This is sometimes known as the sensitivity of a test, right? So, for example, if you are getting tested for some kind of disease, right? So whether it's a COVID test or, you know, some kind of disease screening, all right? If you actually have the disease, we want the test to detect it, right? And so a test with high power will detect anybody who has the disease, right? If somebody has the disease and the test detects it, that will be a test that is powerful. And we know that the, you know, COVID tests aren't 100% powerful, right? A lot of times you can take a test and they come with disclaimers that says, you know what, it's possible that you just got infected, but because it's only like your first day after infection, that there isn't enough virus level in your, you know, the nose or wherever it is that they've taken your thing. And so you might get a negative test, but it doesn't mean you're actually free from infection. It could just be that, you know, it's too early on to detect it, right? And that a lot of tests are like that, right? If the virus level is not high enough, the test is going to come back negative, even if there actually is an infection. And that's just that's not specific to just coronavirus. That's a lot of tests. And so, you know, there is a limitation in power. It's very difficult to get something that's 100% powerful. Okay, you know, similar with say pregnancy tests and things like that. So pregnancy tests are looking for certain hormones that are present in the urine, and that hormone might not be at a high enough level until, say, you know, a few days after, you know, there's implantation on the uterine wall and things like that. It might not be, so a person could technically be pregnant, but might still result in a negative test, right? There's limitations in power. So a very powerful test will be one that will correctly reject the null, will give you a positive result anytime the null hypothesis should be rejected, right? So a test is considered powerful if you're confident that it will correctly reject the null hypothesis when it's supposed to, right? As in the test will correctly detect a disease or whatever else is known. No, okay, sensitivity of a test. There is a relationship between the t-test and the confidence interval, right? And I said, I think I alluded to this, and I said these two things are mathematically equivalent. They're kind of like two sides of the same coin. So if you conduct a non-directional or a two-sided t-test, with alpha equal to 5%, this is equivalent and is going to make the same conclusions of making a 95% confidence interval. And if you conduct a t-test, a hypothesis test with alpha equal to 1%, that would be equivalent to making a 99% confidence interval, right? So if the if the hypothesis test for some data ends up with p-value less than alpha, then that means we reject the null hypothesis, and our conclusion is going to be that mu1 is different from mu2. We're going to say mu1, the null hypothesis is that they're equal, the alternative is that they are unequal. If your p-value is less than alpha, we come to the conclusion that mu1 is unequal from mu2. If you were to take that same data, and if you were to create a confidence level with confidence level 1 minus alpha, right? So if it's a 5% alpha and you create a 95% confidence interval, then that confidence interval will make the same conclusion that mu1 is different from mu2, right? And so what must be true about your confidence interval if you come to the conclusion that mu1 is different from mu2? What must be true is that that confidence interval does not contain 0, because that's when we conclude that the two means are different, right? If the confidence interval does not include 0, we say we have evidence that mu1 is different from mu2. And so that would be the case if you created a confidence interval for that same data. Does that kind of make sense? So let's try out an example here, okay? And I've intentionally written very little information in this exercise, okay? We're going to say we're going to perform a hypothesis test with alpha equal to 5%. Okay, so we're going to perform a hypothesis test, and we come to the conclusion that we should not reject the null hypothesis. Okay, so what can we say about our p-value in this scenario? So yeah, that our p-value is greater than alpha, okay? All right, so our null hypothesis will be that the two things are equal. The alternative will be that they are unequal. And our p-value, whatever it is greater than 5%, okay? Because we said do not reject the null hypothesis. Now, we don't know exactly what the p-value is. It could be 7%, it could be 20%, it could be 50%. We have no idea, okay? So all we know is that we don't know the p-value, but we do know it's greater than 5%. Okay, so here's a few questions. What would happen if we use the same data set, same test, but this time alpha is 1%, okay? So our p-value is greater than 5%. So what conclusion if alpha is equal to 1%? Okay. So how does my p-value compare to alpha? Okay. Well, my p-value must be greater than alpha, right? My p-value, whatever it is, it's bigger than 5%. Even though I don't know exactly what it is, if I ask, is it greater than 1%? Yes, absolutely. So we come to the same conclusion. Do not reject the null hypothesis. Okay. What would happen if alpha were 10%? Okay. If alpha were 10%, the answer is we don't know. Okay. The p-value may or may not be greater than 10%. Okay. It could be 7%, and we would end up rejecting the null hypothesis because p-value is less than alpha. It could be 15%, and we would not reject the null hypothesis because the p-value is greater than alpha. So we don't know, okay? So p-value may or may not be greater than 10%, so we don't know the conclusion. Okay, all right. If we take the same data and we were to make a 95% confidence interval, right? So that we're going to use the same data, we have where the p-value ends up greater than 5%, will a 95% confidence interval for this data contain 0? Yeah, the answer is yes, right? Because the answer here is do not reject the null, right? So do not reject the null means we do not have evidence that mu1 is different from mu2. Okay, so the confidence interval will make the same conclusion which means a 95% confidence interval, the confidence interval contains 0, right? When the confidence interval contains 0, that means we do not have evidence of a difference. Okay. This is good with everybody. All right, and so a 99% confidence interval will contain 0. Also, because it corresponds to the 1% alpha, whereas a 90% confidence interval might or might not have 0. Might or might not might or might not contain 0. We're not sure, right? Because it's going to be the same thing as making a 10% alpha, right? Also, if you think about it, so here's your 95% confidence interval, and we're going to say 0, this interval contains 0. If I make it wider, it has to contain 0, right? Because here, if this is the 95% confidence interval and we have 0% in there, if we go from 95% to 99%, the 99% interval will definitely also contain 0. Okay? Whereas on the other hand, if your 95% interval contains 0 and you make it more narrow, then the resulting interval may or may not contain 0. We don't know without more information. Okay, and so I think I put all of those answers right here, which you can review on your own time there. And so you can definitely expect a handful of questions kind of like this on your quiz this weekend. So you'll have an upcoming quiz going over a lot of these kind of conceptual ideas with the hypothesis tests. I mean, you'll have to do some hypothesis tests yourself, along with answer some conceptual questions related to it. And you can expect to see some questions like this. So if you want to put a little star in your notes that says, whatever this is, slide 33 or slide 18. It's numbered slide 18, but I think it's the 33rd slide in the slide deck. Okay. I guess any questions before I go on? Is 1 minus the confidence interval alpha? Yes. So 1 minus the associated alpha is equal to 1 minus the confidence level, right? Or 100% minus the confidence level as a percentage. Yeah. So 99% confidence interval corresponds to alpha equal to 0.01. Yes, that is a question. Or alpha 10% corresponds to 90% confidence interval, so on and so forth. Okay. Maybe I'll just backtrack a little bit. there is no direct relationship between alpha and beta. Just because you know alpha doesn't necessarily mean you can calculate beta right off the bat, okay? So there is a relationship where decreasing alpha increases beta, but it's not a direct one-to-one relationship. And so we are not going to cover power calculations, but if you were to take another statistics course or another kind of research methods course, you might have to do some power calculations. And so the power of a test is given by 1 minus beta, but the calculations of that are a little bit more complex, and we're not going to be covering them in our course. There is a relationship, reducing alpha increases beta, increasing alpha reduces beta, but it's not a direct one-to-one relationship. Okay. Okay, and then another question in the chat, just making sure an alpha of 5% means upper tail probabilities of 2.5% on both sides. Yes, so an alpha of 5% for a non-directional test, which is what corresponds to a confidence interval, would correspond to 2.5% on two tails that when you combine them add up to 5%. Yeah, so yes. If the exception is when you're doing a one-sided test, then it's just on one side. So this is an important kind of mantra that we always bring up in statistics courses, is that you might find an association between variables at the end of your study, right? So you have something that you're measuring, say height, and you have some kind of grouping variable, you know, genders or something, or maybe it's something else, right? I think in the textbook you have like, you know, I don't know, some kind of measurement, and it's based on, you know, one group versus another group, right? At the end of your study, you might find out that there's a difference between the means, right? Group 1 has a different mean than group 2, right? Population 1 is associated with a larger mean than population 2. Okay. Now it's important to note that just because you do find an association doesn't mean that one thing causes the other. Okay. You can't say that just because somebody belongs to this group, that's going to cause them to have a larger or smaller variable than someone else in the other group. Okay. So association does not mean causation, right? If you especially if it's an observational study, all we can say is that there's an association, that being in this group versus that group is associated with having a larger or smaller mean than the other. Okay. And again, we're not saying anything about individuals. Individuals could be large, have high or low values compared to their own group's mean. So as far as an individual go, you can have somebody who's tall or short compared to their own group mean, or, you know, whatever else that we're measuring here. Okay. If you do want to make a cause and effect conclusion, you need to have data that came from a randomized experiment where we are able to assign treatments to each person, right? We're able to assign things. So certain things we cannot assign, right? For ethical or practical reasons, we cannot just force somebody to, you know, begin using some medication if we don't have their consent and things like that. So so certain experiments are just not possible. But if you are able to conduct an experiment with randomized assignment and things like that, then you might be able to draw a cause and effect conclusion. Just to kind of reiterate. All right, we'll continue on here, and I'm going to introduce non-parametric tests, and we will look at non-parametric tests today, and also next week, Monday, we will look at a few non-parametric tests as well. So the t-test that we've been talking about so far is known as a parametric test, okay? And that's because there is mathematical theory behind the t-test that effectively says the sampling distribution can be approximated with a normal distribution. right? We looked at sampling distributions, we looked at the central limit theorem, we said all of this stuff, and we said effectively it can follow, the sampling distribution follows a normal distribution. And the reason why it's called parametric is because the normal distribution is known as a parametric distribution in that it's defined by parameters. You have the mean of the population, you have the standard deviation of the population. Those are parameters, and any kind of theoretic distribution that's defined by parameters will be a kind of a parametric distribution. Any test that relies on that will be a parametric test. As far as our class goes, we've only learned, kind of two theoretic distributions, the normal distribution and the binomial distribution. But again, there's lots and lots and lots of different probability distributions out there. And if you do take more statistics, you'll learn about some of them. But as far as this class goes, we only learned the binomial and the normal distribution. That's fine. Normal distribution, the parameters that define the normal distribution are your n and your p. Okay, your sample size n and the probability of a success p defines your binomial distribution. Okay, but anyway, there are a few conditions that must be true in order to apply the central limit theorem. Okay. First, our samples must be selected independently and randomly. Okay, so that kind of holds for almost all of these tests that that we use. And again, I have the caveat that this is actually kind of hard to pull off in real life. So as you're reading a study and you think, could this even be considered a random sample? Maybe you have to question the results of the study. Okay, but kind of the thing that we can really scrutinize under the central limit theorem is that the sample size must be large enough. And I think there was an example in your homework where you did not have a sample that was large enough. Okay, the sample must be large enough. Okay, and what that means is if the population is normal, any sample size is large enough. So if you look at your data, it seems like it's normal, you don't have any outliers, you could get away with that using a small sample. Okay. On the other hand, you need to have a large sample size over 25, if the population is not normal. If these conditions are met, as in the sample is independent and random, and the sample size is large enough, which either is this case or this case down here, then we can assume that the normal distribution approximates the sampling distribution, and we could use the t-test. Okay. But if they're not met, right, if these conditions aren't met, then using the t-distribution could end up leading us to make the wrong conclusion. And so to avoid that, in a situation where these conditions aren't met, we might prefer to use a non-parametric test, right? You can, like a lot of the topics we cover in our course, you could really dive deep into these things, okay? And so you can take an entire course on non-parametric statistics. And as far as this class goes, on this slide I wrote, we'll learn just one test, but that's actually not true. We'll learn a total of 3 non-parametric tests. We'll learn a total of 3 non-parametric tests. We've got the Wilcoxon-Mann-Whitney test, which we'll cover today. And then next week, we'll look at the sign test and the sign rank test. So a total of 3 non-parametric tests. But again, that's just a small drop in the bucket of this whole separate world of non-parametric statistics, okay? So the Wilcoxon-Mann-Whitney test is used to compare 2 populations, right? And we have to be careful about the words we're going to use, right? We're going to say if 2 populations tend to produce similar values or different values, okay? It would be a non-parametric alternative to the t-test. So the t-test is used to see if 2 populations have the same mean, and the Wilcoxon-Mann-Whitney test is used to see if 2 populations have similar distributions, okay? Now, in general, non-parametric tests are going to be less powerful than parametric tests, okay? Because non-parametric tests make no assumptions about the sampling distribution. The t-test assumes the sampling distribution follows a normal distribution, okay? The t-test says the sampling distribution follows a normal distribution. We're assuming that, and therefore when I see this unusual value, I can make all sorts of other assumptions and come to a conclusion, right? We're making a lot of assumptions when we do a t-test. When we use a non-parametric test, we are making very few assumptions, okay? We're not going to jump to any conclusions. And so in order to come to the same conclusion, it requires a lot more data, So again, going back to the analogy of like whether you should hang out with a person or not, the t-test is going to be the one that just, a couple incidents is enough to just say, let's reject the null hypothesis, right? We see the person be rude with the wait staff one time, and we go, that's enough. We don't need to hang out with this person anymore, okay? The non-parametric test, the Wilcoxon-Mann-Whitney test says, you know what, let's give everybody the benefit of the doubt. This person was rude to the wait staff and it was a bit of a turnoff, but you know what, maybe this person was just having a bad day or something. We'll give them a second chance or something like that, okay? So that would be the non-parametric test. It requires a lot more data to come to the same conclusion of rejecting the null hypothesis, okay? So because it is less powerful though, in general, we would only want to use the non-parametric test or Wilcoxon-Mann-Whitney test if the sample size is small and there are present outliers present in your small sample, right? So if you have outliers and the sample size is small, then you should use the Wilcoxon-Mann-Whitney test, right? Because in other cases, right, if you have no outliers and you have a small sample, you might be able to say, you know what, my data might come from the normal distribution, okay? And if you have a big sample say is 25 or more, even if you have outliers, you can say, well, because my sample is so big, I can assume my sampling distribution comes from the normal distribution. But if you have a small sample and you have outliers, then you don't want to assume that the sampling distribution is normal, and we would use the Wilcoxon-Mann-Whitney test, okay? There is another test known as the Wilcoxon rank sum test, and they are mathematically equivalent, even though the process to come to a conclusion is a little bit different. Okay, any questions on this? Does this kind of make sense? This criterion, only use the Wilcoxon-Mann-Whitney test if the sample size is small and you have an indication that it's not normal, meaning you've got outliers present in your small sample. Okay, so I'm using an example straight from the textbook. And the question is there a difference in soil respiration of kind of two areas, the gap and the growth? All right, so I didn't know this was a thing, but apparently if you're like an environmentalist, you can go into the forest and the ground, the soil in the forest breathes off carbon dioxide. Okay, I guess like material is decaying, and part of that process is the organisms in the dirt breathe off carbon dioxide, and you can measure this amount of soil respiration. Okay, and so it's like the moles of carbon dioxide per gram of soil per hour or something like that. It's measured in some strange thing. Okay, and the researchers were curious, is there a difference in the soil respiration if we go to an area of the forest where lots and lots of things are growing? That's the growth area. And then they also went to an area of the forest where there was kind of a clearing, not a whole lot of things were growing. And they were just curious, is there a difference in the soil respiration? Okay, and so the null hypothesis is that the population of soil respiration values for the growth area is not different from the population of soil respiration values in the gap area, okay? Or more succinctly, both populations tend to produce similar values. Now, the null hypothesis has to be this wordy mess when we're doing a non-parametric test, okay? You cannot use words like the mean, okay? There will be no symbols like mu in the hypothesis. There will be no, maybe I should also add, there will be no words like the mean in the hypothesis, okay? This is non-parametric, so add that. There are no words like the mean in the null hypothesis because A non-parametric test makes no reference to parameters like the mean or the standard deviation or these things, okay? We're just talking about the numbers. Are the numbers similar or are they different? We're not saying anything about the mean because these are non-parametric tests, okay? So we don't have a symbolic way to write the null hypothesis. You know, with the t-test, you could just write mu1 equals mu2, right? Simple. You can't do that with a non-parametric test, okay? Non-directional alternative hypothesis would be something like one of the populations tends to produce larger values than the other population, okay? One of the population tends to produce larger values than the other population. Or another way you could say is that there is a non-zero shift between the populations. Like one population is shifted to be higher, so it produces bigger values than the other population, okay? You could have a directional alternative, meaning you would say something like the population from the growth area, you specify the population, tends to produce larger values than the population of the gap area. That'd be directional. Or you could say the population of the growth area tends to produce smaller values than the population of the gap area. Okay, so there you're specifying one of the populations, exactly which one produces larger or smaller values than the other thing, okay? But again, no symbols like mu, no mentions of the word mean or anything like that in your hypotheses, okay? And I will say there is going to be a quiz question where I'm going to ask what are the hypotheses to use for the non-parametric Wilcoxon-Mann-Whitney test. You'll have a few examples. One of the choices will have the word mean, and it's going to be very tempting to pick it because it sounds so much like the hypotheses you use for t-tests, but that's the wrong answer because it's using the word mean, okay? I'm basically giving you the answer here, okay? Yeah, for a non-directional alternative, it just says one of the populations. We're not specifying which one, okay? We're just saying that there's a difference between the two populations. So basically one of the populations is bigger than the other, but that doesn't specify whether we're talking about the growth population or whether we're talking about the gap population. We're just saying one of them is bigger than the other. So that's just saying there's a difference, right? Okay, so here's the process for how it works to actually conduct the Wilcoxon-Mann-Whitney test. Number one, you take your data. You've got two groups of data, right? You're going to arrange them in two columns, least to greatest, okay? And then what you're going to do is for each value, you're going to look at the other column and you're going to count how many values are less than that particular value. And if you have a tie in the other column, then we'll count it as a 0.5, right? So you say, okay, 1, 2, 3 values are smaller. 1, 2, 3, 4 values are smaller, something like that. If you have a tie, you'll say like 4.5 values are smaller, okay? And then you're going to add up these counts for both of the columns. And we're going to look, at least for our textbook, whichever is the larger of the two sums, that's going to be our Mann-Whitney U-test statistic, okay? And then we go to our reference table and we're going to look this up. So let me do this. So I'm following the example in our textbook, and let me just go ahead and I have the numbers here, but let me we'll work through this, okay? Okay, so these are the numbers from our data, okay, arranged from least to greatest, okay? So we had, we're looking at soil respiration for the growth area and the gap area. And so for the growth area, the smallest number is 17, 20, 22, 20, 64, 170, 190, 315. And then for the gap area, the numbers go 6, 13, 14, 15, 16, 18, 22, 29, okay? And the two samples are of different size, and that's okay. Okay, so we have growth, we have a total of 1, 2, 3, 4, 5, 6, 7 values. And for the gap, we have a total of 1, 2, 3, 4, 5, 6, 7, 8 values. Okay, and it's fine that you have two samples of different size. And we want to use the Wilcoxon-Mann-Whitney test because if we look at this, we look at the spread of values for these numbers, like we have a number like 315, that seems like an outlier. Okay, it's quite different from the other numbers that we have. So this would be an indication that, yeah, maybe we got to use the Wilcoxon-Mann-Whitney test. Okay, so we're going to go for each number. We look in the other column and we say, how many values are smaller than this number? So our first number is 17, and we go to the other column. We say, how many numbers are smaller than 17? Okay, and we go, okay, 1, 6 is smaller, 13 is smaller, 14 is smaller, 15, 16. Okay, so that's 1, 2, 3, 4, 5 numbers are smaller than 17 in the other column. Okay, we go to the other one, right? 6, so the next number is 20. So 6, 13, 14, 15, 16, and 18. We have 6 numbers in the other column that are smaller than 18. Okay, then we have 22. Okay, so we go through and we go 1, 2, 3, 4, 5, 6 numbers are smaller, and then we have a tie at 22. So I'm going to write 6 ties are worth 0.5. Okay, if there were multiple 22s, each of those 22s would be 0.5, right? So if we had 3 22s, we would say, 0.5, 0.5, 0.5, and we would end up getting something like 7.5 or something. So each tie is worth 0.5. Okay, and then we get to 64, and we say, oh, all 8 numbers in the other column are less than 64. Okay, we look at 170, all 8 numbers in the other column are less than 170. 190, all 8 numbers in the other column are less than 190, and 315, all 8 numbers are less than 315. Okay, so one thing to note is what we're going to do is we're going to sum up this column. We do 8 plus 8 plus 8 plus 8, 32. 6 and 6 is 12. So that's what, 44.5 plus 5. We get 49.5. Okay. One thing to note, this is my one potential candidates for test statistic, is that all 4 of these numbers, 64, 170, 190, 315, all 4 of them contribute 8 towards this test statistic. Okay, this last number, it didn't have to be 315. It could have been 1 million. Okay, it could have been 1 million, and my test statistic would have still been 49.5. Right? It could have been, it could be anywhere from 30 to 300,000 to a million, and my test statistic would be 49.5. It didn't actually matter how big this number was. Okay, so an analogy that sometimes people use for non-parametric statistics, especially a test like this, is that the values don't actually matter. It's just kind of the rankings or the comparisons that matter. And an analogy is parametric statistics are like business, non-parametric statistics are like sports. Okay, so if you think about a sports game, it doesn't matter whether a team wins by 1 point or a team wins by 50 points, it's still a win, right? So you might say, oh, this, if you got a basketball game, the game could end up being like 80 to 81, and then the team that got 81 scores a win, right? It could also end up being 80 to 130, okay? And it still counts as a win, right? It doesn't matter if they won by 1 point or 50 points, it's still a win, and that's how it goes. Okay, whereas in business, the actual numbers matter, right? If you have a quarter where you lose money, right? Maybe you lose $100 in the quarter. Okay, that's one thing. Versus another quarter where you lose $10 million. Okay, it's losing $10 million is a lot more financial trouble than losing $100. Okay, and so the actual value actually does matter in business. Okay, and so but in non-parametric statistics, it didn't really matter if this was 315 or 1,000 or 30. It would have contributed to 8. Okay, and so whereas if you were to calculate the mean of these numbers, it would make a big difference whether it was 315, 1,000, or 30. Okay, whatever that number was, it would make a big difference as far as calculating the mean. Okay, so anyway, back to this. We do the other column. We say, okay, how many numbers in the other column are smaller than 6? Okay, none of the numbers. How many numbers are smaller than 13? None. 14, 15, 16, none of the numbers are smaller. At 18, one number is smaller. At 22, 17, 20, and we have a tie. We're going to get 2.5. And at 29, we have 3 numbers that are smaller, okay? So we add these up, and our sum is going to be 6.5. Okay, so we take these two numbers and we go, oh, 49.5, this is going to be my test statistic mu. Or not mu, u. Wilcoxon-Mann-Whitney, my test statistic is 49.5. Okay, and we're going to look this up in the Wilcoxon-Mann-Whitney table. All right, so let me go ahead and pull that up. It's one of the pages in your reference tables. Reference tables. Here we go. Okay, so oh, that's too small. It's table 6, critical values and p-values for the Wilcoxon-Mann-Whitney test. All right, and on the left-hand side, we need to find an n and an n prime. Okay, so the n and n prime, you have two n's. And so whichever is bigger, so I have n2 is 8, n is going to be 8, and n prime is going to be 7, okay? So whichever number is bigger is going to be your first n, and then whichever number is smaller between your two n's is going to be the n prime. So we're going to have n is 8 and n prime is 7. So I'm going to go down to the row where n is 8, n prime is 7. This is the row I'm in, okay? And we're going to look up this number 49.5. So the numbers in bold are the test statistics. And so, so if we got 48, our p-value would be 0.021. If we got 50, our p-value would be 0.0093. But we have 49.5, so it's not one of the values exactly. Okay, so in our case, our p-value is between 0.0093 and 0.021. Okay, 0.021. Our p-value is between 0.021 and 0.0093. Okay, now this would be a non-directional p-value. So we didn't actually specify whether we're using a directional or a non-directional alternative. Okay, so if we just said, is there a difference? Is there a difference? We would have the non-directional p-value. Okay, now it's a little bit confusing, so always read the top of your table. Okay, so the top of the table says directional p-values. Right? I'm sorry. This table provides selected values of the test U statistic in bold type and corresponding p-values for a non-directional alternative in italics. If you have a directional p-value, directional p-values are found by dividing the number in italics in half. So always read this heading, and what it says is, well, if you have a non-directional alternative, your p-value is the numbers we found in the table, which would be 0.021 and 0.0093. 49.5 is in between these two numbers. So our non-directional p-value is there, okay? Oops. Okay, so we do this, and our non-directional p-value, again, is between 0.021 and 0.0093. So if we choose a non-directional alternative, right, this would be our conclusion. Our p-value is between 0.021 and 0.0093. If alpha were 5%, our p-value is less than alpha, and we would reject the null hypothesis, okay? We would say, we have evidence that the two populations produce different values, tend to produce different values. And furthermore, because when we look at our data, we see the test statistic for the growth area being 49.5 versus 6.5 for the gap area, we would say, furthermore, not only are they different, but we could say the growth area produces larger values than the gap area, okay? So our alternative started off non-directional, but you look at the data and you go, oh yeah, the growth numbers are bigger than the gap numbers, okay? Do we not use the 6.5? So our table, the table in our textbook uses the large number and we get 49.5. There are tables in different textbooks that use the smaller one. And so it just kind of depends how the table was set up. Our table is set up to use the large values. So we're going to use the 49.5. But 6.5 is a number as well. And if you have a different Wilcoxon-Mann-Whitney table, you might use the 6.5. But in our case, we use the 49.5. Okay. So that's what we would conclude. So we can say we have evidence that the soil from the growth area produces higher respiration values than the soil from the gap area. Okay. We could have a directional alternative. And if this directional alternative were that the growth area produces larger values than the gap area. Okay, our test statistic is 49.5. We check the p-value for a directional test, and we would take these numbers and we would divide this in half. So 0.021 divided by 2 gives me 0.0105. Is going to be my directional p-value, greater than my directional p-value. And I do 0.0093 divided by 2, and I get 0.00465, right? 0.093 divided by 2, 0.00465. So my p-values for a directional test would be between basically 1% and 1/2 of 1%, okay? 1% and 1/2 of 1%. And if alpha were 5%, we would reject alpha, we would reject the null hypothesis, and we would come to the conclusion that we have evidence that soil from the growth area produces higher respiration values than soil from the gap area. Okay. And then it's a little bit strange to think about, but it is also possible that you have the wrong alternative, that the growth area produces smaller values than the gap area. Okay. If this were the case, we would actually not even have to bother looking up values in the reference table, okay? Because when we do the statistic, we get 49.5 for the growth and only 6.5 for the gap area, okay? So our data does not support the alternative that the numbers from the growth area are smaller than the numbers from the gap area, right? Because if we look at my numbers, the numbers in the growth area are bigger than the numbers from the gap area. So if somebody says, do we have evidence that the growth area produces smaller values than the gap area, we would say no, we don't have that, right? If that were the direction of the alternative we chose, okay? So in that case, we would say the data does not align with the directionality of the alternative hypothesis. My data shows that the growth numbers are bigger than the gap numbers. So if the alternative said the growth area produces smaller than the values in the gap area, no, we don't have data to support that. The sum of the growth area is greater than the sum of the gap area. This indicates that overall the values of the growth area are larger than the values from the gap area. And we would say we do not have evidence to support the alternative hypothesis. And that would be the conclusion there. What difference between the two sums would be considered significant enough for one to be larger than the other? Okay, so the question in the chat is, here we got one difference over here, which was 49.5, and the other difference was 6.5. And the question is, well, what kind of number is going to be big enough? And the answer is, it depends on the sample size, and that's all given in the table. So you have to kind of go through the sum, and you have to look up, right? So if you have a small sample size, like a sample size of 4 and 4, a difference of 16, okay, which basically means all 4 numbers in the in one table are bigger than the other all 4 numbers in the other side, that would result in a big enough sample, right? If you have big samples, right, like samples of size 11 and 10 or 11 and 11, then at say a sum of 91, that will be big enough, okay? And sums that are smaller, like a sum of 81, won't be big enough or something, okay? So it depends on your sample size and to kind of make this conclusion. All right, question, what if the test statistic is a whole number? Does it give it an exact p-value? Yeah, so if you get your test statistic, like if we did this, so in our case, we got 49.5, but if your test statistic ended up being one of these numbers, right? Like if instead of 49.5, we got, what was it, 8 and 7? Let's say we got 48. Okay, so we do the thing, we compare the numbers and we get 48. Then your number right here is just going to be, your p-value is 0.021, and that's it. There's no range. Your p-value is 0.021. So if you got one of the numbers that show up in bold in this table, that's just going to be your p-value. Okay, and it's just only if you don't get a number that's in the table, right? So if you get 51, your p-value is 5%. If you get 54, your p-value is 2.1%. If you get 53, it's something in between there and there. Okay, and that's just because we're using a paper table. A computer is able to kind of compute these out a little bit better, right? But that's not what we're doing. Oh, let me give you your last view quiz answer for today, and we'll call it an evening here. Okay, so last view quiz answer for today is the letter A. A as in apple. A as in apple is your last view quiz answer for today. A as an apple. Question, what if for the last example, the two test statistics were really close, like 49.5 and 48, then even if growth is still larger, we'd still have to look at the reference table. Yeah, you still have to look at the reference table. And technically, when you do these comparisons, because you're always counting like how many numbers are greater than in the other table, it ends up being, the product ends up being 8 times n1 times n2. So the sum of 49.5 and 6.5 is 56, which is always going to be 8 times 7. It's always going to be the two numbers multiplied together. So so yeah, if you get so to get something like 48 and 49.5 or something, that would only happen if you have what is 48 and 96. You'd have to have two sets of numbers that multiply out to say 96 or 100, like maybe a sample size of 10 and 10. And in that case, if you have a sample size of 10 and 10, it only starts to become significant when one of the samples was up to like added up to 77 or something like that. So so it's, you know, something like that's unlikely. Okay, 12 and 8 would be added to 96 and only significant at say sum of 74. So yeah, always use the reference table and things like that. Okay, so once again, last view quiz answer is A as in apple, and we will end here for today. So have a good night, and we will see you guys later. Okay.